This is the second part of our homework 2 tutorial, the nature of regression. This corresponds to question 2.2 and 2.3. For any regression analysis, most of the time we would start from an event or phenomenon that we are interested to study. Let's call it Y. And we are curious about how Y is generated. So for this reason, we assume that there is a data generating process that gives rise to Y. We assume this process exists and takes a form like this. Notice that there are two parts in the data generating process. One is the systematic part, and the other is the stochastic part. Let's first take a look at the systematic part. This is what we call the population regression function, or the theory. It describes a relationship between X and the conditional mean of Y. So for example, if Y is income, X are wage, are age, and education, we would say in theory, if a person has a high level of education, we would expect on average that person also has a high level of income. But in reality, this may not be necessarily true, because a person may have a low level of education but still earns a lot of money. That's the difference between YT and the conditional mean of YT. So the population regression function really describes an average relationship between X and Y. So that's in the average sense. But the real Y also depends on a stochastic term. So the model itself, or the theory, may exclude a lot of variables that also affect Y, and we all aggregate those terms or variables into the stochastic term. Because there's a theorem called the central limit theorem, which says if there are large amount of variables, random variables aggregated together, the resulting variable will follow a normal distribution. So that's why most of the time we would assume that the stochastic error term follow a normal distribution, because it includes a lot of unspecified variables. And if we put them together, we get the stochastic population regression function, and it is also called the data generating process, so they are equivalent. But most of the time, people won't distinguish a stochastic population regression function with the population regression function, and that's why many confusion comes up. So to be precise, we call the whole equation a stochastic population regression function, and we call this deterministic part the population regression function. So from this data generating process, we get the generated data. Because of the stochastic nature of this process, we know that YT, or the value of YT, are unpredictable. But this generated data is what happened in real world. From the perspective of an individual, suppose Y is income, we may say that this person receives this amount of income. But from a perspective of a researcher, we don't live with him or her, so we don't observe this number. So we have to go through a measurement process to collect information on Y. But this measurement process may be subject to error. Those errors can be random or systematic. Later on, we will see how to correct those errors made in the measurement process. And if we don't correct them, they may affect our regression analysis and the estimated coefficients. But for now, let's assume that this measurement process is non-problematic, or we only have random error. And for the example of income, we may say that the researcher collect all the tax documents of the households, and then they get information of their income. So we get observed data, and based on those observed data, we run a regression analysis, and we get a sample regression function. So a sample regression function is just an estimated population regression function. So how do we select the sample regression function? Because from a population regression function, beta may take any value. So it could be any real number. So we have to select some best sample regression function from all the possibilities and get a good estimate. How good it is depends on the criteria that we put forward at the beginning. So next chapter we will talk about what those criteria is. But for now, we can just think of the sample regression function as the best estimated population regression function. And the residual is literally a residual. It is a difference between the real y and the estimated y. So it is a byproduct of the regression analysis. The residual may have certain properties simply as a result of the regression analysis, regardless of how the data is actually generated. So that's the difference between the stochastic error and the residual. The stochastic error is some real unobservable and quantities that we have to make assumptions about, given the based on the model specification. It is a theoretical construct, but the residual is just some byproduct of the analysis. If the model is specified correctly, then we may use the residual to make inference about the properties of the stochastic error term. But if the model is specified incorrectly, then the residual is not a good estimate of the the unobservable stochastic error term. So we have to be cautious about how the model is specified, and this is a very important part of the regression analysis. So the last point is that we have to be aware of the fact that the data generating process is unknown. So we never know what is the true data generating process. We know that from a theory. So if the theory is wrong, it means the data generating process is wrong. Then the whole structure will break down. So that's why we have to be very cautious about how our theory is specified and constructed, and then how we can use them to guide in our data analysis. And this is the end of our section.